Hello and welcome everyone to today's video. This is Lauren from Studyclix, and today we'll be looking at 2021's higher level question 14 part A, which focuses on simple harmonic motion. This part of the question is worth 28 marks and should take approximately 10 minutes to answer. So let's begin. So in order to calculate the first couple of parts of this question, we are given a lot of information about the system at hand. So we're told that an iron sphere of mass 40 grams, highlighting mass 40 grams, it hangs from a spring and oscillates with simple harmonic motion, which is great because now we can use the simple harmonic motion formulae. And we're told that the period of the oscillation is 0.74 seconds. So, in part one, we're first asked, what is simple harmonic motion? You can either give the verbal or the mathematical definition, as you're usually allowed to in physics. So, first, I'm just going to show you the verbal notation, which is perfectly fine, which is that the quality for simple harmonic motion is that the acceleration or the restoring force, they're directly related, is directly proportional to the displacement from equilibrium, and this quality proves that a system is in simple harmonic motion. And this will give you 3 marks. Now, for those of you more mathematically inclined like myself, I give you the mathematical definition. I would include both of these formulae if you are more mathematically inclined like myself and would tend to style your answers in this way, because we are talking about the acceleration and the force. I know they are directly related and one infers the other, but just to make it explicitly known to the examiner of your understanding of simple harmonic motion, state both. That would be my top tip. Also, you can find these formula as shown in the formula and tables book as well. Now, 3 marks you will get for the relevant equations, but also you must remember to notate your mathematical formulae, i.e. put labels on all of the variables in question just to cover yourself, paying in particular attention to restoring force, displacement from equilibrium S, and acceleration. The angular frequency and the spring constant are just constants in these cases, so pay particular attention to these 3. So now we are asked to calculate the spring constant, and we know that the spring constant is denoted by K. So what is K equal to? K is equal to what? This is what we're looking for. So what variables do we have and what variables do we need? So we have the variables M and we have the period T, and we know that the mass, or M, is equal to 40 grams, and the time is equal to 0.74 seconds. Now, even though we don't know which formula yet we're going to use to find K, we know that whatever formula we use, we're going to have to use both of these variables at hand because that's the only information we're given. We're going to have to convert our mass from grams to kilograms because we need to work always in SI units when converting quantities. So, dividing this by 1,000, we get 0.040 kilograms. That's the conversion. Seconds is SI units, so we're fine. So now all there is to decide which formula do we use. Well, there isn't one specific formula. We have a couple. Our first formula is F is equal to ma. The second formula is Hooke's law, which we saw earlier. I'm highlighting K because that's what we need. We saw this simple harmonic motion acceleration formula earlier. And another new formula is T, or the period, is equal to 2 pi over omega. So when I'm always doing simple harmonic motion questions, I always write down as many formulae as possible, and we're going to try and find a connection between these 4. We already know where the middle 2 formulas come from. Where do the other 2 come from? The classic Newton's F is equal to ma can be found on page 50 of the formula and tables book under force and acceleration. And our equation for the period in relation to the angular velocity can be also found under simple harmonic motion on page 54 of the formula and tables book, where we can highlight it here. Now, just by writing down a collection of formulae, we get 3 marks, and the 3 marks specifically go to this formula over here. Now, how do we relate these formulae? Well, we know that we can equalize the forces so that MA is equal to minus KS. And we know what A is equal to over here. This is why it's a really, really good idea to write down as many formulae as possible. So we have minus M omega squared S is equal to minus K. Now we can cancel a load of things here. We can cancel these, the minuses, the S's. So we are left with M omega squared is equal to K. And that's the formula we're going to use. This formula right here, which we have derived, will get you another 3 marks. Now we need to find out what omega is. We can find out what omega is through this equation up here because we know the period. So we can rewrite the angular velocity in terms of the period, and therefore we could submit in our numbers 2 pi over 0.74 seconds. Now, which is that? Putting this into our calculator, making sure everything is correctly inputted, and we get the angular velocity to be roughly 8.49 radians per second. And this gets you another 3 marks. Now we have the angular velocity, we have the mass, we can finally find the spring constant. So K is equal to mass omega squared, which is equal to 0.04 multiplied by 8.49 squared. Let's put this into our calculator. Now I'm going to keep this number in our calculator as follows, so that when we clear the screen, we have the mass times the answer in brackets squared. Always do brackets when you have powers because we don't want the calculator to get mixed up. Be extra careful. And this is equal to 2.88 Newton meters. To give you your final 3 marks, not forgetting our units, because if you forget your units, you will lose marks. Now we're asked to calculate the acceleration of the sphere when its displacement is 18 millimeters. Just noting that we're going to have to convert that to meters because that's not SI units, from its equilibrium position. Now, S, the variable, stands for the distance from equilibrium. So, S is equal to 18 millimeters, which is equal to 0.018 meters. Now, what formula are we going to use? So what do we have and what do we need? Well, we need to find the acceleration, and we know from simple harmonic motion that the acceleration is equal to omega squared s. And we already know omega squared because from the last question, omega squared was equal to 8.49 squared. Now I'm just submitting in values and we can get our answer. Let's put this into our calculator. We get 1.297, or to approximate 1.30 meters per second. Now, how are the marks split up? The marks are split up as follows. 3 marks for the formula, 3 marks for the answer with our units. Simple. Now, we are given a little bit of extra information. So the system is changed and the iron sphere and the spring are brought to rest, and a small magnet is attached to the sphere. So there's a bigger mass. So when the magnet is attached to the sphere, the length of the spring increases by 15 millimeters. And we are told that the acceleration due to gravity is 9.8 meters per second, which should give you a hint as to how you will problem solve your way out of this question. So I've drawn a diagram to the left here where we have the 2 springs, the spring in its original state and the new state over here. So the total state is in equilibrium. That means the forces up equal the forces down, as we can see. So what are the forces down? The forces down is just equal to the mass times the acceleration in the downward direction, which is just equal to minus mg. Why am I putting a minus here? Well, the acceleration is acting downwards, and if we're going to take down as negative, then of course the acceleration is going to be negative. So forces up, that's going to equal the restoring force, which is minus ks. Now, because we're in equilibrium, as I said, the forces up equal the forces down, i.e. minus m, which I'm going to highlight in red because that's the variable we want to solve for. G is equal to minus ks. They cancel. So we just have mg is equal to ks. Now, just marks broken down thus far. We have 3 marks for either stating F is equal to mg or F is equal to minus ks. And we have another 2 marks for equalizing the two forces, because that's a key concept of it being in equilibrium. I'm basically rearranging this formula. Now, we already know what K is. K is equal to 2.88. We are told in the question that S is equal to 15 millimeters, which is not in SI units, but like as we did in the previous part of the question, we divided by 1,000 to get 0.015 meters. So we have these two. And we also know G is equal to 9.8 meters per second. So we are good to go. So the mass is equal to, when everything is solved and subbed in. Now let's take out our calculator. Subbing in our values, not forgetting any brackets along the way. And there we have it. The mass is equal to 4.4 times 10 to the power of minus 3 kilograms. If you would like to write this in more compact form, which I suppose you do, you can notice that K, in this case in kilograms, i.e. kilo, not to be mixed up with K, the spring constant, that is equal to 10 to the power of 3. Now, when you multiply 10 to the power of 3 by 10 to the power of minus 3, they just give 1. So in reality, we just have that the mass is just 4.4 grams. Not forgetting our units, that gives us our final 2 marks, and we are done the question. Now, moving on to part B, which focuses on hydroacoustics and the Doppler effect. This part of the question is worth 28 marks and should take approximately 10 minutes to answer. So, let's begin. So, in part 1, we are asked specifically, what is the Doppler effect? This is worth 5 marks in total, and 2 keywords, or phrases if you like, will get you your full marks. What are these 2 phrases? So, in reading out the definition, the apparent change in the frequency of waves due to the motion of the source or the observer relative to one another. Even though the full statement, this full definition must be stated, you get your marks 2 for apparent change and 3 for relative to one another. In part 2, we're asked to describe how the Doppler effect can be demonstrated in the laboratory. And the marks are broken up as follows. You get 3 marks for your apparatus, your 3 marks for your method, and 3 marks for the observation. You can see that I have my diagram here on the left, and it is showing that we have an electronic buzzer and it's moving around in a circle. Somebody is at the center of this circle, here, and they're swinging it around and around. And we have our observer here, which will detect what frequency they observe or hear, or etc. So the electronic buzzer is swung around at different distances relative to the observer, keyword being relative to the observer, and the observation being that the buzzer's pitch frequency increases as it moves towards the observer and decreases as it moves away. So going back to our question, why have I done that? Well, we are given more information regarding the next part of our question. So a moving underwater source emits, keyword emits, a sound frequency of 800 kilohertz while traveling towards, keyword here, an underwater detector which detects a frequency of 806 kilohertz. And we're asked to calculate the speed of the source. So, what formula do we use? What variables do we have? and overall what do we need to find within this formula. So, of course, since we're going to find the speed of the source and the whole topic is about the Doppler effect, we are going to use the Doppler effect formula, as you can see on my left here. And we need to find u, the speed of the source, which I've highlighted again in red. Why have I highlighted the minus sign instead of the plus sign? Well, we're going to need to use the minus sign in the denominator in our formula, and here's why. We were given the very, very useful information that the source was traveling towards the detector, which means that the observed frequency, as you can see by comparison over here, is going to be larger than the actual frequency, i.e., our observed frequency is greater than the actual frequency, which means that the denominator needs to be as small as it can in order for this whole relation to be true and relevant to what we were answering in the question. If it was traveling away, the denominator would be larger and we'd use the plus. But in this case, we use the minus. Now, why have I highlighted in red the prefix K? I've highlighted K because we are not in SI units here. Hertz is also equal to seconds to the -1, which is an SI unit. But kilohertz is not an SI unit. And because we're going to be converting from one quantity to another quantity, we're going to have to go into SI units. So 800 kilohertz, multiplying it by 1,000, gives 800,000 hertz. And we use the same logic with F prime. Now, C, or the speed of sound in water, is 1,480 meters per second. I got this at the bottom of our question. So, where did I get this formula? I got it on page 59, as you can see here, under the Doppler effect of the formula and tables book. Okay, so before I sub in any values whatsoever, I'm going to manipulate this formula as follows. Well, first of all, we can rewrite it as this because we don't need the plus. That's irrelevant here. Multiplying both sides by C minus U, expanding our brackets, and bringing U to one side. Now taking out a factor of C on the left side and dividing through by the apparent frequency. And there we have it. We have a fully manipulated form for U. Let's sub in our actual numbers now. Taking out our calculator, let's sub in our values. Be wary of all the zeros you're using. And using a bracket here. And our answer is 11.017 meters per second. Not forgetting our units. Now I'm going to round this just to 2 decimal places. And not forgetting our units, of course. So, how are the marks broken down? You automatically get 3 out of the 9 marks for this question just by stating the formula, i.e. just copying it down from the formula and tables book without needing to learn it off at all. Putting in our figures and manipulation, that's another 3 marks. And of course, our final answer is also going to be 3 marks, giving us 9 in total. Now, we're nearly finished with this question. In part 4, we're asked to draw a ray diagram to show the refraction of a sound wave as it travels from water into air. If you go back to the question, it actually gives you a little bit of information before part 4 saying that sound waves travel faster in water than air. Basically how this is because in water a lot of the molecules are jiggling around, they're fluidly moving about, whereas in air they're sparsely populated. So that means because sound is a longitudinal wave, there is more chance for the molecules to vibrate and the sound energy to be transmitted through the medium. Now, from you studying light, you'll know that in a denser medium, the ray of light will bend towards the normal. And air is the denser medium in this case. It's the opposite for light. So I have at my normal here, my air medium, water medium, the media boundary, and we have the sound of wave in water and moving into air. Now, how are the marks broken down? You basically get 2 for stating and showing that the sound wave bends towards the normal, and 3 marks for showing that it changes direction, i.e. here, when it's going from one medium to the other. Now moving on to part C, which focuses on the photoelectric effect. This part of the question is worth 28 marks and should take approximately 10 minutes to answer. So, we better begin then. Okay, so in the first kind of section of this question, in parts 1, 2, and 3, we're asked to describe what happens when we vary either the frequency or the intensity of the light in this experiment. And we're told beforehand that the frequency exceeds the threshold frequency, which is an important factor in the photoelectric effect experiment. Okay, so in part 1, F is constant, but the intensity is increasing. So the first thing you have to say in order to get your first 2 marks in this part is that more electrons are emitted. Why is that? Well, we know that the photocurrent is directly proportional to the light intensity. So if the intensity increases, the photocurrent increases, and which directly means that more electrons are emitted. And for your next 2 marks, you have to say that the electrons have the same energy and speed, and this directly relates to the frequency being constant. Because as we know, frequency is related to energy, and if we've no change in the frequency, we've no change in the kinetic energy, and therefore the speed of the electrons. Okay, so in part 2, the frequency in this case is increasing, but the intensity is constant. So the same number of electrons are emitted, and this follows directly from the first part of our question. And for your next 2 marks, we have to say that the electrons have a greater energy or speed, because as we know, frequency is directly connected to energy, therefore it's connected to kinetic energy, which means it's connected to speed. Given the equation, kinetic energy is equal to 1/2 mv squared, and you'll be able to find that in the photoelectric effect equation, which we'll showcase later in the video. Now in part 3, it's a little bit different. We are told that the frequency is lower than the threshold frequency, but F is kept constant and the intensity is increasing. And for 4 marks, no electrons are emitted. That's the statement, and this follows directly from the fact that the frequency is lower than the threshold frequency, and the electrons do not have enough energy to move or be excited or to leave the metal. And this follows from the photoelectric effect. So, moving on to parts 4 and 5 of this section of our question, we are told that the light of wavelength 440 nanometers, which constitutes to lambda, is incident on a metal that has a work function, which is constituted by the Greek letter phi, of 2.6 electron volts. And we have 2 parts now to complete with this information. Part 4, calculate the threshold frequency of the metal. So a part of Einstein's photoelectric law, we have a definition of the work function which we have been given. And that is phi is equal to h f0, where h is Planck's constant, f0 is the threshold frequency, and phi is the work function. We are told that phi is equal to 2.6 electron volts. But when we're converting from one quantity to another quantity, we have to use SI units. An electron volt isn't an SI unit, so we're going to have to convert that. And the conversion is as follows. To go from electrovolts to joules, we need to make the conversion that 1 EV is equal to 1.602 times 10 to the minus 19 joules, which means that performing our calculation, we have phi is equal to 2.6 times 1.602 times 10 to the power of minus 19, which is equal to, taking out our calculator. Remember, always use brackets when you're especially dealing with scientific notation, making sure we have the minus up here. And we get this here as our work function in joules. Now, already on this page, we have 3 marks because of the formula, which we took down. And where can we find this formula? You can find this formula on page 59 of your formula and tables book. Under Einstein's photoelectric law, there's our value for our work function. So we have our work function in joules. We have Planck's constant, which can be found under the universal physics constants on page 47 of your formula and tables book, which is this small number here. And we have our formula, which we can manipulate to give us an expression for the threshold frequency. Plugging in our values. I've also put in the units when I'm subbing in values because it's good to see if your units match up with your answer, then you're more likely to be right. We know that the units for frequency are hertz, which is also equal to seconds to the minus 1, which is what you get when you divide through here, because S is on the denominator. So let's put these values into our calculator and we can get our answer. Now, as you can see up here, I've kept the value of phi, the work function, up on our screen. So now it's going to be stored as an answer. So we can have answer over our expression for h, which is 6.626 times 10 to the minus 34. Be careful of your index on the scientific notation here. So there we have it. There is our answer. You can either express it in seconds to the minus 1 or hertz. I've rounded it to 2 significant figures here, and that gets you your final 3 marks. Now for part 5 in this section of our question, we're asked to calculate the maximum speed of the emitted electrons, and where can we get this value from? Or we can get it from Einstein's photoelectric law. So we're going to have to find V max, or velocity max, which is the maximum speed here. Phi is the work function. F is the frequency of the light. We have our Planck's constant here, and we also have the mass, and that is going to be the mass of an electron because that is the particle in question. And where can we find this formula? Well, we can find it on the same page as our last formula, which we used in part 4. You can find it on page 59, again, in your formula and tables book, again, under Einstein's photoelectric law, just here. We have the work function value, and I'm going to keep it in joules. We were originally given it in electron volts, but again, we're going to be converting from one quantity to another quantity, so we're going to have everything in SI units. We've already calculated this in joules in the last section. Planck's constant is the same as before. The mass is just the mass of the electron, as stated previously. That is the particle in question. And you can find this on page 46 of your formula and tables book under fundamental physics constants. We want to find V, but we don't have the frequency. What is that? However, we were given the information of the wavelength. And the wavelength, or lambda, was equal to 440 nanometers. Nano, in this case, means times 10 to the minus 9. And we want everything in SI units, i.e. meters. So that is just equal to 440 times 10 to the minus 9 meters. That's our lambda. How can we find the frequency through this? Well, we know that frequency and wavelength are related through this equation here. F lambda is equal to c, where c is the speed of light, for which the value of c is equal to 3 times 10 to the power of 8 meters per second, which can be found on page 47 in your formula and tables book. This is the rounded version here. We know what lambda is, we know what c is, and we can finally find what f is. Rearranging our formula, and now we just sub in our values. Let's put this into our calculator. Remembering to check your prefixes as you go. And we get this as our frequency, 6.8 times 10 to the power of 14. Checking that our units are correct as we go along. So now we have everything to find our velocity. So I'm just going to rearrange Einstein's photoelectric law, because before I sub in any values whatsoever, I want to get an expression for V. Now, this is a kinetic energy term. We already know Planck's constant and the frequency, and of course, the work function. Again, when you're dealing with large numbers, like you'll see how I will do this in the calculator, I always have loads of brackets because we've so many indices and scientific notation going on. It is really, really helpful to do that, and you will be guaranteed to make less mistakes. So I actually have the frequency up on screen. So again, this can be stored as an answer. So we have Planck's constant. Our answer is stored as the frequency. And we have our work function. And this is our answer for the energy, the kinetic energy, which is roughly 3.5 times 10 to the minus 20 joules. Getting our expression for Vmax. Vmax squared is equal to 2 times this value, rearranging this formula, over the mass of the electron, m, which, rearranging this and subbing in our values, we can get a value for Vmax squared. Putting this all into our calculator, as you can again see, I've put our kinetic energy term, which is the 3.5 times 10 to the power of minus 20, up on the screen. That's going to be stored as the answer in the calculator. That's a kind of a tip. It's just saving things and it makes your answer more accurate, which is nice. I'm putting the mass on the bottom. We have this as our velocity max squared. Now let's square root this to get Vmax, keeping it as our answer. And there we have it. I'm going to put this in scientific notation and round to 2 significant figures. And we have 2.8 times 10 to the power of 5 meters per second. Now, I used multiple formulae in this, and where will I get it from? The frequency wavelength relation can be found again on page 59 of your formula and tables book under the velocity of a wave. So you don't need to learn this off at all. And now I'm just going to show you the breakdown of all the marks. For your first 3 marks, stating of the Einstein photoelectric effect formula. Next 3 marks for our frequency wavelength relation. We get our next 2 marks from our answer for the kinetic energy. And finally, with our units, not forgetting them, we get our 2 marks for the maximum velocity. Now moving on to part D, which focuses on light and refraction. This part of the question is worth 28 marks and should take around 10 or so minutes to answer. So let's begin. So for part 1, we're asked to draw a ray diagram to show how an inverted image is formed in a lens. And we're asked whether the image is real or virtual. Now, the key phrase here is inverted image. It gives us oodles of information. And if you remember that an inverted image always implies a real image, then it'll basically help you figure out this part of the question. So an inverted image always constitutes a real image, and that gets you your first 3 marks out of the possible 12 marks for this section. Now, because we have a real image, we need to use a converging lens, and that gets you another 3 marks. And you can see that from the oval shape of the lens. Because in a diverging lens, which is the other type of lens, images are always virtual and upright. So you physically can't have a real image in a diverging lens, so it must be a converging lens. Now, in order for us to have a real image, the object must be outside of the focus. If it was inside of the focus, we'd have a virtual image. And that gets you another 3 marks. And this is why it's very important to label your object and your image, which I've done here. And your last 3 marks go for correct rays shown. In order to have an image, we need to have an intersection of rays. And the image is formed at the point of intersection, as you can see here. So we need to have 2 rays. The first ray shows that the law, this ray over here, shows the law that if you have a light ray going through the center of the lens, there's going to be no refraction. Second ray here, if the light is running parallel to the mirror, it'll refract itself through the focus of the lens. Now moving on to parts 2, 3, and 4 of this question, we are told that the critical angle of the glass in a ball lens is 41.4 degrees. And for part 2, we are asked what is meant by critical angle. And the answer is as follows. The critical angle is the angle of incidence to which the angle of refraction becomes 90 degrees when light is travelling from a denser to a rarer medium. The key word being denser to a rarer medium for the angle of incidence, and those 3 things together will get you your first 3 marks. And for your second 3 marks for the definition, we have to state that the angle of refraction becomes 90 degrees, giving you a total of 6 marks. Okay, so moving on to part 3 of this section of our question, where we're asked to calculate the speed of light in the ball lens, very much focusing on the word in here. Okay, the only bit of information that we are given, which is enough to answer this question, by the way, is that the critical angle, C, is equal to 41.4 degrees. Given this information, 2 formulae in particular come to mind, which I'm going to write down here. So these 2 formulae for the refractive indexes, and you can find these formulae. I've used a little bit of different notation here, as you can see. I've labelled that this is the speed of light, C, in the air of the vacuum, over the speed of light in a particular medium, in which case this is our ball lens, which is probably going to be glass or plastic. That's kind of the material that lenses are made out of. Given by the picture, I'm going to guess it's glass, but that doesn't really matter. We're not asked that. You can find these formulae on pages 59. As you can see here, we have the refractive index in terms of the 2 speeds of light. We have C1 and C2 here, but because we're looking at the speed of light going from air into glass or another medium, and that kind of defines kind of the refractive index normally in that sense, we're going to put C1 is equal to speed of light in air or the vacuum. They're virtually the same, which is a fundamental physics constant that we are given. And the other formula, which is the refractive index, again, it's expressed a little differently, and is equal to 1 over sine of the critical angle. You can find that on page 60 of your formula and tables book. Okay, so moving on with the question, because we have one quantity, which is n, our refractive index, equal to an expression of some kind over here, but we also have the same quantity equal to another expression, we can equate these 2, giving us this expression here. Now we know the critical angle, we have that up here, but we also know the speed of light in air or vacuum. This can be found, this is little c. Try not to mix them up. So little c for air, that is equal to roughly 3 times 10 to the power of 8 meters per second. And that can be found in your formula and tables book under fundamental physics constants. It's pretty well known. I'd try and learn that kind of figure off at the back of your head, because it comes up a lot in every single kind of topic wise to do with light or photoelectric effect or modern physics. It just comes up a lot. So it's kind of nice to know it. If not, that's okay. We always have the formula and tables book just for confirmation as well. Just to tally up the marks that we have so far. So for stating either one of this formula here or this formula here, you get your first 2 marks. For noticing that these 2 are equivalent, you get another 2 marks. The next step is basically plugging all of your answers in together to find what we are looking for, which is the speed of light in the particular medium, i.e. the ball lens, whatever material that is. So now I'm just going to rewrite it as follows and manipulate this expression. So we just get the variable we want on one side equal to a product of the 2 values that we do know, which are c and the speed of light in air. We're going to plug in our values here, And let's just put them all into our calculator. So, using brackets, I always find this helpful, just so you get everything kind of nice and neat. Especially be careful with the brackets of sine, because you could pull up a syntax error and need to do double brackets at the end. So we have 41.4 degrees, making sure that at all times your calculator is set with the degrees button, because if it's in radians, the angle, it'll calculate a completely different thing. We're given the angle in degrees, and up here you can see the little d here. So we know that the calculator will calculate or recognize what's in the trigonometric identity as degrees. And there we have it. I'm going to put this in scientific notation and round to 2 decimal places or 3 significant figures, because this expression is messy. But it is roughly on the same magnitude scale as the speed of light in air, meaning it is of the same magnitude. They're both times 10 to the power of 8, which kind of gives you a rough inclination as to the correctness, I suppose, of your answer. And always do these kind of little checks during the exam, because if your answer makes sense, it's more likely to be right. Also, please don't forget your units. They're in meters per second, and there's no excuse to forget them because you can find them all in the log tables. And for calculating this final value, you get your final 2 marks. Okay, so moving on to part 4, this section of our question. We're to explain why white light is dispersed as it passes through the ball lens. Okay, so basically white light is what's called polychromatic light, which means it's made up of many, many, many different colours of light. And by many, I mean 7, which you should learn off by heart. And because we have different colours of light, white light is made up of many different colours of light, which all have different wavelengths. And therefore, by Snell's law, they have different refractive indexes. And therefore, they disperse differently. They bend, they have different angles going through the glass. As you can see in the diagram here, obviously it's not drawn to scale or anything like that, but the red light here, it diffracts the least because it has the longest wavelength, whereas the violet light here, it has the shortest wavelength, so it diffracts the most. And I have here that white light is coming in, incident, it splits, and then they all disperse out upon entering the air again. Where your mark's going to be built up, you have to state that white light is made up of many different colours. That's 2 marks. And that they have many different refractive indexes for each colour of light. And that's why they are dispersed.